Hi students, welcome to KTU Web. We've been dealing with a video series in riveted joints, and in my previous video I'm already discussed about how can you design riveted joint, what are the fundamentals of selecting riveted joint, and what are the types of joint that you can have. In this video I'm going to discuss about one of the famous and useful application of riveted joint. As you could see in these images, that are boilers and pressure vessel. In boilers and pressure vessel, it is not recommended to use welded joint because welded joints will alter the property of that materials due to elevated temperature upon weld. So instead of weld, we oftenly use riveted joint in pressure vessels. As you could see in these images, there is numerous number of riveted joint in this pressure vessel. So for the design purpose, we are classifying these kind of joints into two. As you could see in this figure, the first kind is, as I am marking right here, that is along the circumference of that container. So when it is along the circumference, we call it as the circumferential joint. And similarly, you can also find there is a longitudinal rivet in this pressure vessel, that is which is parallel to the longitudinal axis, and these kind of riveted joint what we call as the longitudinal joints. The design process of these different types of rivets is differ from each other, and in this video I am going to discuss about how can you design the longitudinal joint for pressure vessel, and that is pretty much very common in problem. For a cylindrical container with a high pressure steam inside, it is expecting that high pressure steam will apply stresses on the inside wall of that container. Due to this intense pressure within the container, there will be a pressure development inside that container. That stress what we call as the hoop stress. Similarly, in case of spherical containers, you can also have the hoop stress due to the internal pressure of steam or any other kind of fluid in it. It's also known as the hoop. By using the fundamental equation from solid mechanics, we can derive the equation for hoop stress. In case of a cylinder, it is given as the hoop stress sigma is equal to pressure inside the container into diameter of container by 2 times of thickness of the plate of that container. And similarly for spheres, sigma is equal to Pt by 4T. So these are two governing equations which will give you an idea about how much stress will be developed within that container. And here we are going to deal with the cylinders, since most of the boilers are in a cylinder shape. From this equation we can easily write the thickness of that sheet will be equal to, that is T is equal to pressure into diameter of that cylinder. That is what the diameter, you can have the diameter here, this is what the D, divided by 2 times of the stress. So this is what the equation for the thickness of that plate. The thickness should be equal to this much. But when it comes to rivets, we have to consider efficiency. So when you consider an efficiency eta, we cannot have an exact thickness as per the 100% stresses. So we can consider the value for efficiency as well as, that means the thickness become equal to P into D divided by 2 times of hoop stress into efficiency of that rivet. And there is another value as well, plus you have to consider the corrosion allowance, and this allowance is basically given to account the corrosion that we expecting within the service life of that boiler. The corrosion allowance is normally in a range of 1 to 3 mm. That means we are taking 1 mm extra because we are expecting a rate of corrosion within 10 years or 20 years and so on. So So that will be given in your problem, otherwise you can assume. So this is the basic equation that we are going to use to get the thickness of boilers or otherwise the pressure vessels. Okay, let us deal with a question and you will understood how can you use this kind of equation to solve problems. Design a triple riveted double strap with equal width longitudinal butt joint for a boiler shell of 1.5 meter diameter. The maximum steam pressure is in the boiler is limited to 2.4 megapascal. The rivet pitch is to be same for all rows and all are chain riveted. The allowable stresses in tension, shear, and crushing are given by 124, 93, and 165 megapascal respectively. Take a corrosion allowance in thickness of plate as 1 mm. Okay, this is the problem that we are going to solve. Hope you watched my previous video regarding the riveted joints. Here we have a different kind of question. The question is specifically asked for the riveted joint for boilers or otherwise pressure containers. Okay, let us check with the given data. The first one is the type of rivet. It is a triple riveted double strap with longitudinal joint. That is what we are going to solve, and this is what the longitudinal joint as we discussed. And then we have another extra information that which was not available in previous question, that was the diameter of this shell. So we have to design a boiler with 1.5 meter diameter, and the steam pressure is given as 2.4 megapascal. So the steam pressure is basically what we call the hoop stress that we experienced within that container. And we have the other three stresses or the capacity of riveted joint that we are expected to get: 124 megapascal in tear, 93 megapascal in shear, and 165 megapascal in crushing. These are the fundamental requirements to design any kind of rivet. Okay, we can start from the step 1. In step 1, we are going to get the type of joint. The type here is given in this question as the butt joint with the triple riveted double strap, and it is an equal cover chain rivet. So triple riveted double strap means we have three set of rivets or three rows of rivet within a single plate or single master plate, and it is a chain rivet. There is no zigzag or staggered, and cover plates are equal. So this is what the cover plate number 1, this is what the cover plate number 2, and this is the master plate number 1, and this is master plate number 2. Two master plated are edge to edge connected, that is what butt joint, and we have a cover plate above and below, and within a plate, within a master plate, we have rivet number 1, rivet number 2, and rivet number 3. So that is why it is triple riveted a double strap butt joint. So as per the type of rivet, you could have a rough sketch regarding how the rivet will looks like. Now we can go for step 2. In step 2, we have to find the thickness of boiler shell. As we discussed in hoop stress equation, it is given by thickness T is equal to P into diameter of that container divided by 2 times sigma T into efficiency plus the corrosion allowance. So this is the basic equation. We already derived this equation and we can apply the values here. The thickness of that shell is given by the pressure inside. It is given in the question as 2.4 megapascal into diameter is given as 1.5 meter, that is 1500 mm, divided by 2 into sigma T is 124. It's given data into the efficiency. Here is maybe little bit confusing for you. There is a standard efficiency that you could find from your data book. For a triple riveted butt joint, the standard efficiency as per the Indian Boiler Act, eta is given by 85%. So you can take that from the data book, that is the standard value, if it is not mentioned in that question paper. So we can give the 85 percentage, that is simply 0.85, plus the CA is what, the corrosion allowance. Here we take corrosion allowance as 1 mm. So upon solving, you will be getting T is equal to 18.07 mm. That is, when we check with the data book, you can find the standard thickness of plate. T is equal to, we are going to set it as 20 mm. So that is all about finding the thickness of plate. T is equal to 20 mm. So this is the separate step which was not available in previous videos. Whenever you are dealing with a pressure vessel or boilers, you have to find the thickness of plate by using this equation. And this particular equation will also be available with your data book. You can check that with the data book that you are using. In this problem, I am using a data book from Mahadevan. You can have any other kind of data books. Now we can jump into step 3. In step 3, we are going to find the diameter of a rivet hole. As you know, the diameter of rivet hole can be found from Anwin's formula. As we did in previous problem, the diameter of rivet hole D is given by 6.325 root of thickness of plate. Here we have T is equal to 20 mm, and hence D is equal to 6.325 root 20. Upon solving, you will be getting D is equal to 28.28 mm. Upon checking with the standard data from data book, the standard diameter D is equal to 28.5 mm. So this is nothing but the standardization of value. Now we get diameter is equal to 28.5 mm. This is what the diameter of riveted hole. From this we can find the diameter of rivet shank. The diameter of rivet will be less than that of diameter hole, and as per the standard it is given as the diameter of rivet, maybe we can denote it as D1, is equal to D minus 1.5 mm. So the diameter is 1.5 mm lesser as per the standard. Since the diameter is fall between 26 and 36, you can use this standard equation from the data book to find the diameter of rivet shank. We will be getting D1 is equal to 28.5 minus 1.5. That is equal to 27 mm. That means the rivet shank will be selected as 27 mm for this design. Then we can go for the fourth step, where we have to find the pitch of rivets. When you find the pitch of rivet, we have to find the optimum pitch and the maximum pitch. And if the optimum pitch is less than that of maximum pitch, we can have that value. And if suppose the optimum pitch is higher than that of maximum pitch, or the maximum possible pitch as per the standard, we have to choose the maximum pitch for proceed with that design. The optimum pitch P is given by the formula from data book, and it is given by P is equal to, so we have this equation, we can apply this numerical expression to find the optimum pitch. Here we have two variables, that is N1 and N2. N1 we called as number of rivet with a single shear, and N2 is the number of rivet with a double shear. Now we have to find number of rivet with a single shear and double shear. You could see in this image, this is a butt joint. That means all the rivets are with the double shear. When we take the rivet number 1, we have double shear. These are two shear planes, and a similar is applicable for rivet number 2 and rivet number 3. We have 3 rivet per master plate, that is triple riveted, and among those 3 rivets we have double shear, and there is no rivet with a single shear. Then the rivet per pitch is another thing. You could find when we take a pitch line, the pitch is marked here, and we take the rivet in between these two pitch lines, and this is the pitch line that is marked in this figure. You can have a half rivet here and remaining half, and similarly we have other parts as well, and that means we have rivet number 1, rivet number 2, rivet number 3, that is half plus half, we have an entire full rivet. That means we have 3 rivet per pitch in this particular design. That we can write here, number of rivet with a single shear is equal to 0, number of rivet with a double shear is equal to 3, and otherwise number of rivet per pitch is equal to n1 plus n2, and it will become 3. So these are the information that we have. Similarly, we can have the value of diameter of rivet hole and the tear capacity, and applying those values in this equation we will get the answer for optimum pitch. Then n1 become 0 and n2 become 3, and upon application we will be getting pitch P is equal to 163 mm, and this is what the optimum pitch of this riveted joint as per the calculation. Similarly, we have to find the maximum pitch as per the standard. The maximum pitch or allowable pitch can be found from the empirical relation. Pmax is equal to K1 into thickness of plate plus 41 mm. Now we have to find the value of K1, and T is given as 20 mm. When you check your data book, you will be getting a table like this. From this table, we can find the value of K1. Here, the number of rivet per pitch, as we found, as we have 3 rivet per pitch, and it is a double strap butt joint. And now we have on the last column that stand for double strap butt joint. And for 3 rivets, we have this value as 4.63. Now we can write K1 is equal to 4.63. That means maximum pitch Pmax is equal to 4.63 into 20 plus 41. We will be getting Pmax as 133.6 mm. This is the value of maximum or allowable pitch for this joint. Now we have to check with the maximum value with the optimum value. Here we are getting the optimum value upon our requirement, upon our calculation as 163. But as per the Indian standard and as per the international standard, the maximum value should be limited to 133. Since in this problem, the optimum value is greater than that of Pmax, you cannot take the optimum value, because when you take the optimum value, it will be greater than Pmax. That means it will deviate the standard. So we have to take a Pmax as the pitch of this rivet. So we will be having Pmax is equal to 133.6 as the pitch of this rivet. And if suppose you are getting an optimal pitch less than that of Pmax, you could take that. Suppose you have optimum pitch as some 120 mm, you can take it because Pmax is higher than that of 120. And that's all. And now we are fixing the pitch as 133.6. Now we can go for the step 5. In step 5, we are going to find the transverse pitch or the distance between the rows of rivet. As per the standard, the transverse pitch PT should be greater than or equal to 2 times of diameter hole, that is equal to 57 mm. Then moving into step 6. In step 6, we have to find the strap thickness. Here in this problem, we have a 2 strap, and upper strap, it is marked as strap number 1, and the bottom strap, it is marked as strap number 2. There is an upper and a lower, that is bottom cover. We have to find the thickness of that strap, and we have some standard set of equation to find it. Since it is an equal strap, we can take T inner is equal to T out, and it will be equal to 0.625 times of thickness of main plate. We will be getting Ti is equal to T outer, and we fixed it as 12.5 mm. On step 7, we have to find the margin of rivet. The margin M means the distance between the extreme end of rivet with the side edge, and margin is always given as 1.5 times of the rivet diameter whole D. We will be getting margin M is equal to 42.75, and approximately we can go for 43 mm. And step 8 is the last one, where we have to find the efficiency of riveted joint for this particular boiler. As you are aware, we have to find the least efficiency among tearing, shearing and crushing, eta T, eta S and eta C. So for that, we are going to find these three efficiencies. The first one, we are going to find eta T, that is the tearing efficiency. I'm advising you to check my previous videos on efficiency of rivet, and we derived that equation to find eta T, and it is given by eta T is equal to pitch minus diameter by pitch. Upon solving, we will be getting eta T is equal to 0.7888, and in percentage we can write eta T is equal to 78.88%. Now we found the tearing efficiency of rivet as 78.88. Then we can go for the next type of efficiency, that is what? The shearing efficiency. We have the expression for shearing efficiency, and upon applying the values, we have N2 is equal to 3 and N1 is equal to 0 as we applied in previous case. Upon solving, we will be getting eta S is equal to 0.9967, and in percentage we can write eta S is equal to 99.67%. Now we have to find the third efficiency, that what? Eta C, the crushing efficiency. The value of eta C is given as, here we have N1 is equal to 0 and N2 equal to number of rivet with double shear, that is 3, and we have the value D and sigma C, as well as pitch, thickness and sigma T. Upon application, we will be getting 0.8428. While converting this into percentage, we can write eta C is equal to 84.28%. Now we can compare these three efficiencies, that is eta T, eta S and eta C. We have eta T is equal to 78.88 and eta S as 99.67 and eta C is equal to 84.28. We have to choose the least one as the efficiency of that joint. That is, we will be getting the efficiency of joint as eta is equal to the lowest value among these three, that is 78.88%. So this is the last step of this problem. We found the efficiency of rivet, this boiler rivet joint, as 78.88. This is the procedure for the most of boiler joints. I will be coming up with new videos as always. Thank you for watching.